Mozzarella begins its life as raw milk, a complex biological fluid composed of water, butterfat, proteins, lactose, and dissolved minerals. This white liquid is a microscopic suspension where water acts as the continuous phase, holding millions of tiny fat globules protected by phospholipid membranes. Suspended alongside the fat are casein proteins, which exist as spherical clusters known as micelles. To transform this fluid suspension into a solid, stretchable cheese, it must undergo a meticulously controlled sequence of chemical reactions and mechanical manipulations. The process starts at the dairy plant with standardization. Raw milk is pumped into a centrifugal separator, a massive stainless steel bowl housing a stack of conical discs spinning at thousands of revolutions per minute. The intense centrifugal force exploits the slight difference in specific gravity between the components of the milk. The lighter cream is forced toward the center of the spinning bowl, while the heavier skim milk is pushed to the outer edge. Proportional valves carefully bleed a precise amount of cream back into the skim line to achieve an exact fat-to-protein ratio. This ratio is critical. If the milk contains too much fat, the final mozzarella will weep oil when melted. If it contains too little, the cheese will become tough and rubbery. Once standardized, the milk enters the pasteurization phase to eliminate pathogenic bacteria and halt any wild fermentation. It flows into a plate heat exchanger, a heavy piece of machinery consisting of dozens of corrugated stainless steel plates compressed together. Cold raw milk flows down one side of a plate, while precisely heated water flows up the opposite side. The corrugated pattern induces turbulent flow, forcing the liquid to swirl and mix, which maximizes heat transfer across the thin metal barrier. The milk is rapidly brought to 72 degrees Celsius and held in a winding stainless steel pipe called a holding tube for exactly 15 seconds. Thermal dynamics dictate that this specific temperature and time combination is sufficient to destroy unwanted bacteria without denaturing the delicate whey proteins. If the milk is heated too aggressively, the whey proteins will unfold and permanently bond to the casein micelles, fundamentally ruining the milk's ability to coagulate into a firm gel. After the brief holding period, the milk flows back through the heat exchanger, transferring its heat to the incoming cold milk, an energy-saving process known as regeneration, before arriving at the cheese vat at a temperature of about 35 degrees Celsius. The cheese vat is an enclosed cylindrical vessel equipped with mechanical agitators. Here, the acidification process begins. A carefully selected blend of thermophilic lactic acid bacteria, primarily Streptococcus thermophilus and Lactobacillus delbrueckii, is pumped into the warm milk. These single-celled organisms awaken in the warm environment and begin consuming lactose, the naturally occurring sugar in the milk. Through the metabolic pathway of glycolysis, the bacteria convert the lactose into lactic acid. As lactic acid is released into the vat, the overall pH of the milk begins to slowly drop. This increasing acidity alters the electrical charge of the milk, beginning the chemical preparation of the casein proteins. With the bacterial culture actively multiplying, the operator adds a highly specific proteolytic enzyme known as chymosin, traditionally derived from rennet. To understand how chymosin works, one must look at the microscopic casein micelles. The surface of each spherical micelle is covered in tiny hair-like chains called kappa casein. These chains possess a negative electrostatic charge. Because like charges repel, the kappa casein hairs keep the thousands of micelles bouncing away from each other, maintaining the milk in a liquid state. Chymosin acts as a chemical pair of scissors. It specifically seeks out the phenylalanine-methionine bond on the kappa casein chain and severs the negatively charged hair. Stripped of their protective, repulsive coating, the micelles are suddenly vulnerable. As they collide in the gently circulating vat, they begin to stick together, bound by naturally occurring calcium ions that act as bridges between the protein structures. Within 30 minutes, a microscopic three-dimensional matrix rapidly forms throughout the entire vat, trapping the butterfat globules and water inside it. The liquid milk sets into a smooth, solid, custard-like mass known as the coagulum. To release the trapped moisture, the solid gel must be cut. Automated mechanical cutting harps, frames strung with fine stainless steel wires in a precise geometric grid, begin to slowly rotate through the vat. The planetary motion of the harp slices the massive gel into thousands of uniform cubes, each roughly the size of a hazelnut. This mechanical cutting initiates a crucial thermodynamic process called syneresis. By dramatically increasing the surface area of the gel, the whey, a yellowish liquid containing water, lactose, and dissolved whey proteins, begins to seep out of the curds. The mechanics of syneresis are driven by the continuous production of lactic acid from the bacteria and a gradual increase in the vat's temperature. Heat and acid act together as a chemical vise, causing the protein matrix within each tiny curd to contract and tighten, effectively squeezing out the whey like a sponge. The speed of the wire harps is meticulously controlled. If they cut too fast, the delicate gel shatters into microscopic curd dust, which washes away with the whey, destroying the yield. The curds and whey are gently agitated and cooked until the curds reach the desired moisture content. The entire mixture is then pumped onto a draining belt or into a drainage vat. The liquid whey falls through perforated stainless steel screens, while the solid curds gather and mat together into a continuous, spongy slab. At this stage, the curds undergo the maturation phase, which is entirely dictated by chemistry. The slab is held in a warm environment, while the bacteria continue to aggressively convert residual lactose into lactic acid. The operator closely monitors the pH level of the curd slab. As the pH drops steadily toward a critical window of 5.2 to 5.3, a profound structural change occurs. At this exact acidity, the colloidal calcium phosphate that gives the casein micelle its rigid internal structure begins to dissolve and leach out into the remaining moisture. This process, known as demineralization, weakens the rigid protein scaffolding. It transforms the curd from a fragile, crumbly state into a highly flexible matrix. Hitting this exact pH target is the most critical failure point in mozzarella production. If the pH does not drop enough, the cheese will not stretch. If the pH drops too low, too much calcium is lost, the protein bonds dissolve entirely, and the cheese will disintegrate into mush when heated. Once the perfect pH is achieved, the curd slab is fed into a milling machine. A high-speed rotating drum, fitted with sharp blades, chops the dense rubbery mat into small, uniform strips. This increases the surface area once again, preparing the curd for the defining step of mozzarella production, the pasta filata, or spun paste process. The milled curds drop into a continuous stretching machine, a long stainless steel trough where jets of hot water, heated to precisely 85 degrees Celsius, flood over the cheese. The thermal energy from the water rapidly transfers into the cold curds. As the internal temperature of the cheese rises above 60 degrees Celsius, the trapped butterfat melts into a liquid oil, and the demineralized protein structure softens, becoming highly pliable. Inside the hot water bath, a pair of massive counter-rotating stainless steel augers grab the softened mass. These screws are designed with a variable pitch, meaning the distance between the threads decreases as the cheese moves forward, gradually increasing the mechanical pressure on the curd. The augers fold, knead, and pull the hot cheese. The physics of this mechanical stretching fundamentally alter the microscopic structure of the cheese. The random tangled coils of casein proteins are subjected to intense shear stress. The continuous pulling action forces the protein chains to unravel and align themselves into long, parallel fibers. As these protein fibers align, they create microscopic longitudinal channels. The liquid butterfat and hot moisture droplets are squeezed into these channels, acting as a lubricant between the sliding protein strands. The cheese transforms from a dull, lumpy mass into a brilliant, shiny, elastic ribbon. The surface becomes perfectly smooth because the protein fibers are completely aligned, sealing the exterior and trapping the fat and moisture within. The continuous ribbon of hot flowing cheese is then extruded into a molding machine to dictate its final shape. A common design is a rotary drum molder. The drum is covered in a specialized Teflon coating, which is chemically inert and has an exceptionally low coefficient of friction, preventing the incredibly sticky hot casein proteins from adhering to the machinery. The drum features multiple cavities machined to the exact volume of the desired cheese block or ball. A mechanical plunger continuously pushes the hot cheese into the passing cavities. As the drum rotates, the edge of the cavity slides past a stationary shear plate, cleanly severing the exact portion of cheese. Because the newly formed mozzarella is hot and highly pliable, it would flatten out under its own weight if left on a table. To lock the parallel protein structure in place, the cheese drops out of the molding drum directly into a cooling flume. This is a long channel of rapidly circulating icy water, usually held around 2 degrees Celsius. The cooling flume often utilizes a countercurrent flow, where the coldest water is introduced at the discharge end of the flume, flowing against the direction of the traveling cheese. This thermodynamic design maximizes the temperature differential between the water and the cheese at all times, ensuring the fastest possible heat transfer. As the cold water strips heat away from the cheese, the melted butterfat inside the protein channels rapidly crystallizes back into a solid. Simultaneously, the protein fibers cool and contract, becoming firm. The swift drop in temperature preserves the spherical or block shape and sets the internal aligned structure. From the cooling flume, the firm mozzarella travels into a brine tank, a deep pool of highly concentrated salt water. Here, the physical principle of osmosis governs the process. The brine contains a high concentration of dissolved sodium and chloride ions, while the internal moisture of the cheese contains almost none. Nature seeks equilibrium across a semi-permeable membrane. The salt molecules migrate from the dense brine into the surface of the mozzarella, while a small amount of residual moisture is drawn out of the cheese. The temperature, salt concentration, and dwell time are precisely calculated. The salt acts as a natural preservative, slowing down any remaining bacterial activity, while also seasoning the cheese and slightly hardening the outer rind to protect the delicate interior. Following the brining process, the mozzarella is dried and prepared for packaging. Fresh mozzarella, which has a higher moisture content, is often packaged in small plastic cups or pouches filled with a diluted brine or purified water. This liquid environment prevents the soft cheese from drying out and maintains its delicate texture. Low-moisture mozzarella, which is cut smaller in the vat and cooked longer to expel more whey, travels to a vacuum packaging machine. The cheese blocks are placed into heavy-duty polymer bags. A vacuum nozzle extracts all the ambient air from the package, and a heated sealing bar melts the plastic together, creating a hermetic seal. The complete removal of oxygen inhibits the growth of aerobic molds, drastically extending the shelf life of the cheese, making it ready for distribution. The true engineering of mozzarella is only fully realized when the cheese is subjected to heat in a culinary setting, such as baking on a pizza. The working principle of the cheese pull relies entirely on the precise chemistry and mechanical alignment achieved during its manufacture. As the ambient heat of the oven transfers into the cheese, the internal temperature rises. At 40 degrees Celsius, the solid butterfat trapped in the microscopic channels transitions back into liquid oil, giving the cheese a glistening appearance. As the temperature crosses 60 degrees Celsius, the casein protein matrix softens and regains the flexibility it had during the pasta filata stretching phase. Because the proteins were forced into parallel alignment at the factory, they do not fracture or snap when pulled. Instead, the long parallel casein fibers slide past one another. The melted butterfat acts as a microscopic lubricant, allowing the protein strands to glide smoothly, while the remaining calcium bridges act as elastic tethers, keeping the fibers connected so the cheese can stretch several inches without breaking. Simultaneously, the residual moisture trapped within the protein channels approaches the boiling point and turns into steam. The expanding steam creates vapor pressure that pushes the flexible protein sheet upward, forming large blisters on the surface of the cheese. As these blisters rise toward the heat source, the surface moisture rapidly evaporates. The exposed, drying proteins and residual lactose undergo the Maillard reaction, a complex cascade of chemical reactions between amino acids and reducing sugars that occurs at elevated temperatures. This reaction rearranges the molecules, generating hundreds of new flavor compounds and producing the characteristic golden brown spots on the blistered surface. The ability of the cheese to melt into a continuous sheet, blister, brown, and stretch into long elastic threads is the direct physical consequence of the controlled acidification, precise calcium depletion, and mechanical fiber alignment engineered into the cheese hours earlier in the dairy plant.